Hello everyone! Thanks for joining our second part of the video, What Algorithms? In the first part, we started discussing algorithms and different goals for different people when developing algorithms. As well as we started thinking what considered to be effective algorithm with focus on its faster running time. Let's move to the next topic, running time, order of growth. In fact, accurate mathematical models are not needed when we focused on algorithms' performance predictions. A rough estimate is used to compare and classify algorithms. Why do we need performance predictions? Remember, we don't know the size of input data when we write algorithms code. Let's assume that algorithm takes care of all input data, which usually is the case. Then if input data size increases, consequently overall program runtime is growing. That comes from the logic that each additional program step, like accessing input data, calculating, writing data, has its time cost. More input data, more steps to do, more time to run a program. Scientists came up with graphical presentation of things for better visibility. Let's use it to analyze program runtime. On horizontal x-axis, let's have problem size, or size of input data. On a vertical y-axis, let's have program running time. When you wrote a program, can you check how long it does take for it to run? In real human life, when for example athletes compete, how to measure their running time on a track to see who is the fastest? We can use stopwatch. Start time counting when athlete starts running and stop right after athlete finishes. Same with running time for a software. You can use stopwatch analogy. Insert two additional instructions in your software code to read computer's time. First one at the very beginning and second one at the very end of your program. Difference between time values will tell you program actual overall running time, our software stopwatch. Returning to graphical representation of algorithm runtime. When your algorithm's input data has just one value, corresponding to number 1 on x-axis, your algorithm takes a certain measurable amount of time to be executed on y-axis. Let's say 2 microseconds. Pair of x equals to 1 and y, 2 microseconds, corresponds to a certain point on our graph. When we have two input values, program will be executed at some, in most cases increased amount of time, which corresponds to another point on our graph. 3 input values at another observed runtime correspond to third point on a graph, and so on. If you connect all dots, you can see certain line pattern, either linear or somehow curved. Since programs usually consistently repeat the same steps one after another during execution, we should expect continuation of the line pattern in case of increasing input data amount. So you collect evidence for small amounts of input data and then making predictions what to expect for larger input data sizes without making actual measurements. Such prediction can be verified on practice with higher values and usually gives more or less accurate expected runtime for any large value. Algorithms usually have several limited number of distinct line forms, differently curved on XY graph. And each of such lines can be described by math formula, which can be simplified for runtime prediction purposes. Special term order of growth classification was introduced, which describes by math simplification how specifically runtime grows when input data size increases. Proportions between data size and runtime is in the main focus. Let's look into order of growth classification with most often distinct examples. The simple case to understand: if we have straight line on our diagram, which means if input data size increases, overall runtime is growing linearly. How is it possible? To simplify, by repeating the same limited set of commands for each input value. Imagine you have set of numbers. For each number, your algorithm executes just the same commands, reads value, multiplies number by itself, and writes results. Each block of commands has the same time cost, let's say 10 nanoseconds. For one value, your algorithm should take 10 nanoseconds, for 2 values 20 nanoseconds, for 3 values 30 nanoseconds, and so on. So you can guess runtime will be increasing linearly. Our linear runtime can be calculated, represented by math function c multiplied by n, where c is the coefficient, the time cost of each block of commands applicable for each input value. Order of growth denoted as function of input data size n in form of O of n for our linear case. It's often named as big O instead of just O. Big O defines upper guaranteed bounds, or the worst case scenario. And it points exactly to proportion between input data size and runtime, how our line in a diagram should look like. Simple n in a brackets tells about linear proportion. We will see what else could be in a brackets later for other proportions. Proportion is in the focus. That's why for simplicity, order of growth discards leading coefficients. Such coefficient does not change proportions or line type. When you see such notation, big O of n, for classifying algorithms' order of growth, that means runtime linearly grows as input data increases. What do you think? Can we have faster algorithm with proportion lower than input data size n? In other words, algorithm's xy line on our diagram will be closer to x-axis, which consequently means that for the same input data size n, algorithm can be executed generally faster than linear algorithm. In fact, such optimal algorithms exist for certain tasks. But how is it possible? The only possibility if your algorithm can skip some input data during execution, but virtually takes all data into consideration, and therefore algorithm still gives you proper final result. Do you remember our analogical example with blueberry farm, where we can have whole rows of bushes marked as very young and therefore not having any ripe berries? So your algorithm can skip checking and harvesting the whole such marked rows with lots of bushes. Skipping some input data speeding up overall runtime and should not affect overall proper result. How effectively we can skip input data and what will be order of growth main proportion? In fact, some algorithms can have big O proportion described as a logarithm of n. Can you see what's inside brackets now instead of just pure n? For those who are not yet familiar with logarithms, take time to understand logarithms basics yourself separately from this video. Important thing for now, curved line on our diagram will be very close to x-axis and runtime growing very slowly, even if number n will be significantly large. It's a huge dream for algorithm developers, because on the large sizes of input data, such algorithms are extremely faster than linear. To visualize possibility, let me bring so-called binary search example, when you try to find certain value in a preliminary sorted set of values in ascending order. Main idea is to divide input dataset into halves. If your value to be found is below the value in the middle of a set, then you just fully skip the right part of a set from further consideration, since it contains larger values because of ascending order. Otherwise, your algorithm should skip the left part of a set. Then you divide respectful part into halves again, and so on. You should not underestimate power of dividing into halves. If you have input data of a size of 1,000,000, on the first step, your algorithm skips half of the million values. On the second step, it skips quarter of the million records, and so on. That's why it takes no more than 20 steps to search for a value in a set with 1,000,000 items, and no more than 30 steps to search for a value in a set with 1,000,000,000 items. While linear brute force algorithm, checking all values one after another, may take up to 1,000,000 or billion steps for each search. Imagine the difference. So logarithmic order of growth is another very efficient class of order of growth for algorithms. Can we do even better? Theoretically, there are constant order of growth algorithms, when algorithms take constant time regardless of input size. But these are very rare cases. Don't expect lots of tasks which could have constant order of growth algorithms. But anyway, how is it possible? You not only need to skip input data a certain way, but literally limit number of commands to be executed every time algorithm works. Kind of the same amount of commands regardless of input data size. Let me bring an example. When you have already preliminary ordered set of values in ascending order, if your algorithm wants to take 3 smallest values, it just needs to read and return first 3 values. There is no need to look into all other values, even if there are millions or billions of them in a set. You know that first 3 will be the smallest 3 values. Since to read 3 values requires specific same set of commands regardless of input data size, such algorithm should take the same so-called constant time. Of course, constant algorithm can outperform logarithmic one on a large set of input data sizes. Big-O notation looks as O of 1 for constant order of growth. It means that proportion between input data size and runtime is constant. And to remind, we discard leading coefficient, leaving just one notation to show constant or same time for algorithm execution. Constant, logarithmic, and linear order of growths are very good in terms of algorithm performance, but there are other heavier brothers. Next one is quadratic with O of n power by 2, big O notation. For example, when algorithm on each step needs to check all pairs of input data. Imagine you have 10 values in your input data set. For example, your algorithm for the first value needs to compare all other values with the first one to find which one is larger. Then the same operation for the second value, all others compared with the second value, and so on for all 10 values. Remember, linear order of growth was linear because for each value you have same amount of operations. For example, 3 operations: read, calculate, write. For current quadratic example, number of operations on each step is dependent on input data size. For simplicity, we can imagine that on each of n steps, number of operations proportional to n. Overall algorithm proportion between input data size and runtime therefore is n powered by 2. Who familiar with software developing can imagine double loop operation or loop inside another loop, which is a good example for big O n power by 2. Again, order of growth focuses on proportions. Leading coefficients are discarded. If instead of just n operations for the first value, you will have 2 multiplied by n operations, or 3 multiplied by n operations, or c multiplied by n in general. For order of growth, leading coefficients 2, 3, or any other c are ignored. Big O notation will look like O n power by 2, no coefficient mentioned. The curve of such line on a graph will be very close to y-axis. For input data size of 10, runtime will be proportional to 100. For input data size of 100, runtime will be proportional to 10,000. You can imagine how runtime will be increasing on a larger input data size. Quadratic order of growth is significantly worse compared to linear one. Another order of growth is a cubic one, with n or powered by 3, big O notation. Instead of constant amount of commands on each step for linear variant with overall proportion to n, instead of checking pairs n power by 2 for quadratic, we are checking triples and having overall proportion of n power by 3 for cubic one. The line on our diagram will be even closer to the y-axis, which means that even for relatively small input data size, algorithm runtime will be very high. These are the main lines and order of growth classifications. Additionally, they also introduced linearithmic classification with O n log n, with the line somewhere between cubic n power by 2 and linear n. Cubic order of growth is something that you need to avoid. It belongs to ineffective types of algorithms. There might be even worse cases. There are lines on our diagram that can be even closer to y-axis. Mathematical functions for them, for example, can be exponential x power by n or factorial n factorial. To simplify with an analogical example, why runtime may be so extremely huge for such cases, you can imagine chess game. On each step you have several chessmen, each can make lots of different moves. Each move opens another new combinations of moves for each chessman. Algorithm can take several steps into consideration before making actual move, like chess master trying to imagine lots of combinations in his mind. And algorithm cannot have predefined number of moves on each step to squeeze within linear, quadratic or cubic scenarios using brute force approach. Therefore, there will be way more steps and consequently extremely high runtime. Most of our order of growth classifications can be in general described mathematically by so-called polynomial. Examples of polynomial are some constant plus another constant multiplied by n, plus another constant multiplied by n squared, plus another constant multiplied by n cubic, and potentially so on. Earlier we mentioned that for simplicity, order of growth discards leading coefficients, while focusing on input data runtime proportion. Similarly, order of growth discards lower order terms, because rather to count all details, we just take into consideration items that are happening most often, more expensive in terms of frequency and therefore overall runtime. As a result, quadratic order of growth, noted as or n squared, ignores linear part, if that exists, because n squared frequency of operations brings more significant impact compared to just linear n on overall input data size runtime proportion. Similarly, cubic order of growth, or n cubic, ignored n squared and just linear n parts, if they exist. So two order of growth simplifications are discard leading coefficients and ignore lower order terms. We still can effectively access proportion between input data size and algorithm runtime. Another thing to mention, outcome was discovered by science. A problem is intractable if it cannot be solved in polynomial time. Polynomial time described by polynomial expression discussed a minute ago. Mentioned exponential and factorial lines on a graph correspond to algorithms which order of growth cannot be represented by polynomial. To clarify with example, what does it mean intractable? If you have 1,000 cities and need to find exactly shortest path for salesman person to visit all these cities using brute force approach, algorithm will take longer than current life of our universe to be executed on any supercomputer. No jokes. So when developing algorithm, our goal is to have polynomial. Among polynomial, try to avoid inefficient cubic order of growth and even quadratic if possible. In general, improving algorithm allows to decrease time in our order of growth sequence. Some cubic algorithms can be improved to become quadratic or even linearithmic. Some linear algorithms can be improved to be logarithmic. It's generally much better, faster. Scientific approach to design and analyze algorithms consists of cyclic iterative activities. Try to develop mathematical models that help us understand properties of the algorithms we are developing. Find working algorithm to solve it. Answer the questions: is it fast enough, thinking about order of growth and runtime? Additionally, out of scope for this video, does it fit in memory? If not, try to test models, experiment and figure out why not fast, doesn't fit in memory, for a goal to find a way to address the problem. Try to improve algorithm, iterate until satisfied, for example in terms of runtime memory. It might be never-ending process for chasing better algorithm though. Some scientific great algorithms were discovered 10, 20, 30, 50 years back, and they're still fastest till nowadays, waiting for someone, maybe you, to probably find another more efficient solution. Let's wrap up what we have discussed so far. Big-O notation is about guaranteed upper bound for algorithm order of growth. There might be other notations like lower bounds, the fastest case of executing algorithm, optimal algorithm, applicable for average input data. Exponential and factorial algorithms are not useful in practice. Among useful, there are distinct curves for order of growth from slowest to the fastest: cubic, quadratic, linearithmic, linear, logarithmic, constant. Always imagine how lines curve for each of algorithm type to realize why it's so effective or in contrary not. Scientific approach is through iterations to find more effective algorithm with curve describing order of growth closest to the x-axis. Why we spent a lot of time to understand order of growth ideas? Remember, when we talked earlier about math models, to accurately calculate running time, we multiply cost of each distinct operation by its frequency. Operation cost depends on system-dependent factors, computer speed and programming language, while operation frequency depends on system-independent factors, input data values and size, and how well algorithm is optimized. Remember that we cannot predict and do not have control over the input data size. In modern world, there might be millions of input items. Computers can execute operations within nanoseconds. But if you have non-optimized algorithm with lots of operations, even speedy supercomputer will spend a lot of time to execute program. Let me provide small table with measured runtime results for regular home computers and supercomputers with higher speed compute power, for two algorithms with different order of growth. We will discuss examples of different sorting algorithms later. Pay your attention on Big O, not their names now. Insertion sort with Quadratic Big-O versus quicksort with Logarithmic Big-O. Both algorithms give proper result, but at a different time. You can see that for billion input data size, even supercomputer will spend 1 week with higher order of growth algorithm, while better algorithm can make it instantly. First important outcome here that optimization of algorithm can have higher impact on overall runtime than computer hardware power. As I mentioned earlier, if you have exponential, factorial Big-O types of algorithms, even supercomputer never could finish it even with input data with size of 1000. Second outcome, making algorithms better is something that we can control and try to implement, if compared to other system-dependent and system-independent factors impacting on overall runtime. Smart algorithms can reduce frequency of operations to speed up overall task execution. That's how we move from slower to faster order of growth types. You can also guess that for small input data size with modern computers' speed, it's not so important which algorithm and corresponding Big-O to be used. But it's very important to apply your Big-O notation knowledge when input data sizes are large. Let me give you a couple real-world examples of algorithms runtime. When I worked for largest telecom operator, I used traffic generator tools to send traffic to mobile network. Absolutely the same task with the same data generated took 15 seconds on one tool to start and 5 minutes on another tool. That's about how efficiently algorithms implemented for the same task. Another example. In April 2019, astronomers and scientists shared to the public the first ever image of a black hole from a distant Messier 87 galaxy. In fact, it was done by calculation on a huge supercomputer based on data from several telescopes, Event Horizon Telescope Array. MIT student Katie Bauman developed the algorithm named CHIRP, which took into consideration 5 petabytes of preliminary collected data. I was not able to find exact number of days for algorithm to work with that data, but my understanding it took several months to calculate results and generate image of the black hole. FYI only. I want to mention that order of growth, our Big-O, is not the only one, but just one out of several commonly used notations in the theory of algorithms. Its main idea is to show proportion between input data size and runtime, and it defines upper guaranteed bounds for any combination of input data values. To give you an idea how to search for other notations if needed, here's an example of another one, Big Omega notation, which develops lower bounds. If Big-O defines the worst case runtime for an algorithm, Big Omega defines the best case. Why we have several cases? Because we don't know what values will be the input data, how they might be preliminary prepared. For example, if you need to sort set of input data, which is already sorted, there will be no need to shuffle, move data by some sorting algorithm, just to check all values are already in the right order. This is about Big Omega, about the best, fastest possible runtime scenario. If input data is sorted in descending order and needs to be sorted in ascending, totally opposite. Sorting algorithm may end up making maximum possible steps to move data within this set to sort it. This is about Big-O, the worst, slowest case. We will talk about sorting algorithms later in this video to show examples of steps numbers and link to notations. Let's summarize common order of growth, Big-O classifications, by naming them and give example of technique, task, which can be used to achieve such Big-O. 1. Constant. Add two numbers. Log n. Logarithmic. Divide in half. N. Linear. Loop. N log n. Linearithmic. Divide and concur. N squared. Quadratic. Double loop. N power by 3. Cubic. Triple loop. 2 power by n, exponential, exhaustive search, check all subsets. To remind, for simplicity, when using order of growth, we discard leading coefficients. The reason is, when input size n is large, coefficients are negligible. When input size n is small, we don't care. Similarly, order of growth discards lower order terms, because rather to count all details, we just take into consideration items that are happening most often, more expensive. See you in the third video.